Hey guys, Mr. Backerberg here. In this video, we're going to look at the first derivative test for local extrema. So a function f might have local extrema at some critical points, but might fail to have local extrema at others. The big thing that we want to look for is the sign of the derivative around a critical point's immediate vicinity. So once we know where our critical points are located, we want to check what's happening around those critical points to help us determine if we're going to have any local maximums or local minimums at those critical points. So there's a test that we can run to help us determine local extrema, and it's called the first derivative test. So this test applies to a continuous function and only a continuous function. So at some critical point C, if your derivative changes sign from positive to negative at that C value, then f has a local maximum at that C value. So here we've got a picture illustrating what's happening. We've got this C value, this critical number, in the middle of our picture, one where the derivative would equal 0, one where the derivative wouldn't exist. On the left-hand side of both of these pictures, the derivative is positive, but on the right-hand side, after that C value, the derivative is negative, so that's creating a local maximum at the top of those curves. Another thing that could happen at some critical point C, if the derivative changes signs from negative to positive at that C value, then our function f is going to have a local minimum at that value of C. So visually what's happening here, again, we've got one picture where the derivative is 0 and one picture where the derivative is undefined. We've got this C value in the middle of both of our graphs. On the left-hand side of the pictures, the derivative is negative, and on the right-hand side of the pictures, the derivative is positive. So that creates kind of this low spot on our graph, which is going to give us a local minimum. Another thing that could happen at our critical point C, if your derivative does not change signs, so if your derivative has either both positive on the left and on the right side of your C value, or both negative on the left or right side of your C value, then our function doesn't have a local extreme value at that value of C. So here, as we're looking at these pictures, we've got critical numbers C in the middle of both of them, but the derivative is positive on both sides, so that doesn't create an extreme value in there. And same thing on this one. Here we've got the derivative being negative on both sides. So again, there's no sign change, so our function does not have an extreme value at C. Now, those first few rules have been dealing with interior critical points, but we also want to look at what's happening at our endpoints of our graph as well. So here we're talking about some left endpoint A. Well, if your derivative is negative for x values that are directly bigger than A, then your function is going to have a local maximum at A. But if your derivative is positive for x values that are to the right of A, then your function is going to have a local minimum at A. So visually what's happening here, we've got this A being the left endpoint of our graph. So on the left-hand side here, we can see a local maximum because our derivative is negative just to the right of A. And over here on the right-hand side, we can see that we have a local minimum because our derivative is positive just to the right of our A value. Similarly, if we're looking at a right endpoint B, then if your function's derivative is negative just to the left of B, then your function f is going to have a local minimum at B. But if your derivative is positive just to the left of B, then your function is going to have a local maximum at B. And again, looking visually at what's happening, we've got a right endpoint for our graph. So in this left picture, we've got a local minimum because to the left of our B value endpoint, the derivative is negative. But here on the right-hand side, at our B value, we've got a local maximum because the derivative is positive just to the left of this B value. So in this example, we're going to look at using the first derivative test to help us find some local extreme values and then identify any absolute extrema as well. So the first function we're going to look at is f of x equals x cubed minus 12x minus 5. Now this is called the first derivative test, so the first thing that we have to do is find the first derivative of this function. So if we just use the power rule in here, that x cubed is going to turn into 3x squared, and then where we've got this negative 12x, that'll derive just into negative 12, and then with that negative 5, that's just going to derive into 0, so we don't need to put the 0 on the end. So the derivative of this function is 3x squared minus 12. Now to find the critical numbers, I want to figure out where my derivative would be 0 or undefined. Well, this one's not going to have any undefined values, but we will have some places where this derivative is going to equal 0. So I'm going to take the 3x squared minus 12 and just set that equal to 0. I would add the 12 over to the right-hand side, so I get 3x squared equals 12. I'm going to divide the 3 over, so we get x squared equals 4. And then I'm going to square root both sides to get rid of the squared power. But when I square root the 4, I have to remember to throw a plus and a minus in front of my answer. So we've got two critical points here. One happening at the x value of positive 2, and one happening at the x value of negative 2. Now, to determine what type of critical numbers these are, we want to look at what's happening around each critical number. And I'm going to draw out a sign chart. So we've got negative 2 as one of our critical numbers, and we've got positive 2 as the other critical number. Well, we want to take a look at what's happening to the derivative around each of these critical numbers. So the first thing I want to do is figure out what's happening on the left-hand side of negative 2. So I'm going to pick a test value from there that I can plug into my derivative. So I'm going to pick negative 3. So in my derivative, I'm going to plug in negative 3. Well, negative 3 squared is 9. 9 times 3 is 27. Minus 12 is 15. And it doesn't really matter what the answer is. It just matters the sign of the answer. We got positive 15, so our derivative is positive to the left of negative 2. Now I want to test something between negative 2 and positive 2, so I'm going to test 0. Plugging in 0, 0 squared is 0, times 3 is still 0, minus 12, we get negative 12. And again, we don't really care what the number itself is, we just care about the sign. It was negative 12, so this is a negative interval for my derivative. And then on the right-hand side, I want to test something bigger than 2, so I'm going to test 3. In my derivative, 3 squared is 9, times 3 is 27, minus 12 is 15. We got a positive answer, so this is positive to the right of that critical number of 2. That behavior that we're seeing in our sign chart helps us determine what type of points these are at the critical numbers. So if we start looking at the negative 2, to the left of negative 2 it was positive, but to the right of negative 2 it was negative. So it's changing from positive to negative at negative 2. So that's going to give us a local maximum at negative 2. But then if we look at what's happening around positive 2, it's going from negative to positive, so that's going to give us a local minimum at the x value of 2. Now, to figure out what those points actually are on the graph, we would have to plug these critical numbers back into our original function. So if we were to take the negative 2 and plug it back into the original function f, then we would get 11 as our answer. So we can say that we've got a local maximum point at negative 2, 11. And then if we want to plug in the positive 2, again, to our original function f, well, if we do that, we'd get negative 21. So we said that this was going to be our local minimum. Now, this function f won't have any absolute extrema because the range for this graph is going to go all the way from negative infinity to positive infinity. If we think about what's happening with a cubic graph, the ends of our graph will keep extending up and down forever and ever and ever. So no absolute extrema, just these local extrema in the middle of our graph. Now if we take a look at this function, we've got g of x equals x squared minus 3 times e to the x. Now this function is also going to be differentiable for all real numbers. So just like we saw on the last one, the only possible critical points are going to be at the zeros of the derivative. So the first thing we have to do is find the derivative of this function. Now, because there's multiplying happening in here, we would have to do the product rule to help us find the derivative. So the x squared minus 3 is going to be my u. The e to the x is going to be v. So the product rule says leave u alone, but then attach the derivative of v. Well, the derivative of e to the x is just e to the x. But then we're going to add, leave v the same, and attach the derivative of u. So the derivative of u would just be 2x. Now we can actually clean this up just a little bit. Since both of these terms have e to the x in them, we're actually allowed to factor e to the x out of there and combine the other pieces using the addition. So then we'd have x squared plus 2x minus 3 times this e to the x. But then we can even factor out this quadratic that's in here, and that's going to help us find the zeros. So if we were to factor that out, this is going to turn into x plus 3 and x minus 1, along with that e to the x on the end. Now, if we're trying to figure out where this derivative is equal to 0, we would take each of these individual factors and set them equal to 0. So if we took the x plus 3 and set that equal to 0, then we would get a critical number at x equals negative 3. If we took the x minus 1 and set that equal to 0, we'd get a critical number at x equals 1. And if we were to take the e to the x and set that equal to 0, this one can't actually be solved. There is no power that we could ever put on e to have this equal 0. So this one isn't going to give us any critical numbers. So the only critical numbers that we have are at negative 3 and 1. So I'm going to make my sign chart. And then we want to test out what's happening around each of these critical numbers. So I want to start by plugging in something to the left of negative 3. So maybe we choose negative 4. Now to do this plugging in with the derivative, I'm going to use my calculator, and I'm going to store key the negative 4, and then I'm going to type out my derivative. When we do that, we get a decimal value of about 0.09. And again, it doesn't really matter what the number is. We only care about what the sign is. It's a positive 0.09, so this is a positive interval on the derivative. Then if we want to test something between negative 3 and 1, maybe we choose to test 0. Again, I would store key that 0 in my calculator and then type out the derivative. And when we do that, we're going to get negative 3 as our answer. Again, the actual number itself doesn't matter, just the sign. This is a negative interval. And then I would want to test something to the right of 1, so maybe we'll choose 2. Again, store key that x value of 2 in your calculator, and then just type out your derivative. I got 36.95 when I did that in my calculator. But again, the number itself is not important, just the sign of the number. So this is going to be a positive interval. Now, checking what's happening with those signs of our derivative, if we look around that negative 3 first, on the left-hand side, our derivative was positive. On the right-hand side, our derivative was negative. So because we're going from positive to negative, we're going to have a local maximum at negative 3. And then if we look at the critical number of 1, on the left-hand side, it's negative. On the right-hand side, it's positive. So that behavior tells us that we're going to have a local minimum at that x value of 1. Now again, we might want to figure out where those points are actually happening. So then we would take each of these x values and plug them back in to the original function. So if we were to take the negative 3 and plug that into our original function, we're going to get about 0.299. So that's going to be our local maximum. And if we were to take the 1 and again plug it back into the original function, we get about negative 5.437. So that's going to be our local minimum value. Now, as we're talking about absolute extreme values. This function maybe isn't as easy to analyze as the cubic that we did initially. So if we're talking about finding absolute extrema here, it might be easiest if we looked at a picture of the original function. So if we were to graph this one out in our calculator, we'd get a picture that looks something like this. So on the right-hand side of our graph, we can see that this line, this is extending up forever and ever and ever. So it's not going to have any absolute maximum values. But what's happening here on the left-hand side, this graph actually has a horizontal asymptote along the y value of 0. So as we extend to the left forever and ever and ever, our function is never going to go below that y value of 0. So where we said we had a local minimum at this 1 and negative 5.437, that's actually the lowest point on the entire graph. So instead of calling that a local minimum, we can call that our absolute minimum. That's going to be it for this video. Thanks for watching.